morning, everyone. My name is Ashu Sharma, Assistant Professor, Department of Computer Science and Engineering, Arya Institute of Engineering Technology and Management. Today, we will see that advantages of frequency domain in image enhancement, what type of impacts over there, and how we can say that it relates with the frequency domain. So, that Fourier transformation is also that is the concept that we cover here. So, first is the overview of frequency domain. Polar coordinate system is a two-dimensional coordinate system in which each of that point on a plane is determined by a distance from a fixed point and an angle from a fixed direction. So here we have, if we see, this is that anti-clockwise, we have this theta, and this is from x-axis, and this is that r, which is distance of this point from this origin. So we have this 60-degree movement that is anti-clockwise, and here we have 210-degree movement for this point. So polar coordinate system is a two-dimensional coordinate system in which each point on a plane is determined by a distance from a fixed point and an angle from a fixed direction. So from this point, that distance is here, and this point distance is here. The fixed point is called the pole. This is called the pole, and the ray from the pole with the fixed direction is the polar axis. So this is the polar axis. So with respect to this, that anti-clockwise we have this rotation. For this point, this is 60 degree, and for this point, this is 210 degree. Now, once we have this overview of frequency domain, f of u is that is equals to mod of f of u multiply e raised to power minus j phi u. Mod of f of u we can calculate like this: f of u, and this is f that multiplication, star multiplication of u, and whole power 1 by 2. So this is simply when we have to take mod of this, and we have this square root of real part and plus square of imaginary part. So it becomes a square root of real part square plus imaginary part square. This is equation number 1. Here star that represent this star represent standard conjugate operation on a complex number. So whenever we say about this frequency domain concept, frequency domain is generally deals with the complex number. Now the equation 1, as per this equation, it is called the spectrum magnitude of the Fourier transform. So from this equation, one thing is clear, that Fourier transform is in the form of that sinusoidal waveforms, and you can say it's a continuous waveform which represent the complex number. Now R of u and I of u are real and imaginary part of this f of u. In image enhancement, we are concerned with properties of the spectrum. Now in the next slide, that we have this phi of u, which is known as phase angle and phase spectrum, and this is equals to tan inverse, that is I of u upon R of u. So equation 2 is referred as phase angle and phase spectrum of the transform. So this is way that we can compute that phase angle or phase spectrum by using this expression. This is equation number 2. Now to compute the power spectrum and spectral density, the square of the Fourier spectrum. So we have to take that square of this mod of f of u, and this is the conjugate, that multiplication with this normal multiplication. So square root that becomes the square, so that cancel each other, and it becomes r square u plus I square u. So when we say about this is that magnitude of the Fourier transform. When we have to compute the power spectrum or spectral density, we have to simply square of this magnitude of f of u. So it becomes r square u plus I square u. Now two-dimensional Fourier transform and its inverse. Fourier transform f of u comma v of two variable continuous function f of xy can be defined as, so here we take u and v as that variable function in these two variables u comma v. It becomes minus infinite to infinite, and minus infinite to infinite, 2 times that integral takes place. F of xy into e raised to power minus j 2 pi ux plus by dx plus dy. So here we have that integration with respect to x and y. Similarly, its inverse can be defined as, so we have to take f of xy is equals to minus infinite to infinite, minus infinite to infinite, f ub into e raised to power j 2 pi ux plus by du dv. So that's change take place over here. Here we have x and y, here we have u and v when we are going to compute the inverse. So fxy, small fxy, that is equals to this following expression. This is for the two-dimensional Fourier transform. Now, for the discrete, when we have discrete Fourier transform function fxy of size m by n, it can be defined as fub is equals to 1 upon mn. And now we have to take this summation unit over here, x equals to 0 to m minus 1, y equals to 0 to n minus 1, fxy e raised to power minus j 2 pi ux upon m plus by upon n. Here u and v are number of rows and number of columns. So here number of rows from 0 to m minus 1, and here number of columns from v equals to 0 to n minus 1. So expression must be evaluated for the values of u equals to 0 to m minus 1, and for the values of v equals to 0 uh, starts from 0 to n minus 1. So these are the rows and number of rows and number of columns. Now, when we have to take the inverse of it, we have just simply put this f of ub inside this summation units like this, and fxy is towards the left hand side. So that expression is evaluated as follows: small f of xy equals to summation u equals to 0 to m minus 1, v equals to 0 to n minus 1. So xy will be replaced by u and v, and this small f is replaced by capital F. And e raised to power, that minus sign will become positive sign, plus sign. So e raised to power j 2 pi within bracket ux upon m plus by upon n. Now this value is x, that is from 0 to m minus 1, and y equals to 0 to n minus 1. So both equation comprise the two-dimensional DFT pair. This expression represents the inverse of two discrete that dimension, you can say discrete Fourier transform. U and V are the transform frequency variable, xy are the spatial variable, which is in general known as image variable. So this is that we have this form. Now the location of 1 by mn is not important. It can be placed in front of Fourier transform. It can be placed in front of inverse transform as well as both transform as a 1 upon under root mn. Now this is that we take that magnitude of FUV is equals to R square UV plus I square UV, and this is square root of that. So the magnitude or spectrum of the Fourier transform. This is the phase angle or phase spectrum of the Fourier transform, tan inverse and within bracket IUV upon RUV, which is the imaginary part and divided by that real part. Now this is the power spectrum. PUB is equals to mod of FUV whole square. So this square root will be eliminated and it becomes R square UV plus I square UV, which is the power spectrum square of the Fourier spectrum. So RUV and IUV, as you know, this is the real and imaginary part of the transform F, capital F of U comma V. Now two-dimensional discrete Fourier transform and its inverse, that is the shift towards the origin, that multiply input image function by minus 1 raised to power x plus y, which is prior to computing the Fourier transform. So f capital F within bracket f of x y multiply by this minus 1 raised to power x plus y, and it is equating that towards capital F u minus m by 2 comma v minus m by 2, where f this dot within this square bracket indicates Fourier transform of the argument. Origin of the Fourier transform f00 is located at u is equals to m by 2 and n by 2, where m and n are, that you can say this is number of rows and columns. Now origin of Fourier transform of fxy minus 1 raised to power x plus y, that is f0 comma 0, is located at this special you can say this position u is equals to m by 2 and v is equals to m by 2, and m by 2 is the center of m by n, area occupied by discrete Fourier transform. This area is referred as frequency rectangle. So if suppose we have a square, you can say that number of rows and columns are equal. So you can replace this m and n together. But we have, this is that position m by 2 is the center in the image having dimension m by n, area that is occupied by DFT. This area is referred as frequency rectangle. So frequency rectangle extends from 0 to m minus 1 and from v is equals to 0 to n minus 1, where u and v are integers. Next, we have the value of the transform at u comma v is equals to 0, 0 is capital F u comma v equals to 1 upon mn. Then two summation unit takes place, 0 to m minus 1 and 0 to n minus 1 number of columns, number of rows and number of columns. And we have this fxy. So now fub is average of small fxy. If small fxy is image, then fub at the origin is equal to the average gray level of the image. So f00 is also referred as the DC component of the spectrum. Thank you so much being with us for this session. We have covered a little bit briefing about the frequency domain, Fourier transform, 2D discrete Fourier transform, how to evaluate inverse discrete Fourier transform, some of the expressions and some of the characteristics of that frequency domain and the Fourier transformation when to be applied in comparison with the spatial domain and frequency domain. Thank you so much.